Okay, I think I'm going to go ahead and get started. Thank you for joining us today. My name is Eric Rule. I'm the Chief Technology Officer here at MMA Design. And I'm today by Andrew Haynes. He's our lead here for all things solar array here at MMA. And also Sandy Sorzano is supporting us. She is our HR and administration extraordinaire. She'll be monitoring the chat session. If you have any questions, please type those into the chat, and she'll be moderating those, and then we'll be covering those questions after we've completed the presentation. Our discussion today is going to be, it's called Delivering More, and the focus is on MMA's Hawk solar arrays. Hawk stands for high watts per kilogram. And MMA has been designing and providing space power solar arrays for CubeSats for more than a decade. We've had power requirements ranging from 300 watts to in excess of 200 watts. MMA also provides a single axis SATA that we've developed specifically for CubeSats. It's a pancake design and it has form factors that are compatible with both the 1U width or the 2U width of a standard 6U or 12U bus. We have flight heritage currently on 7 missions, including Asteria, Shark, Marco, and 11 more that are awaiting launch. And those missions will be covering LEO opportunities as well as lunar and near Earth. And these photos and mission images that I have here on the right, 2 of those won the SmallSat Mission of the Year. The top one is Asteria. And the middle one is Marco, which was a pair of CubeSats that went to Mars. And you can see the solar arrays in both of those. And the bottom one is one I'm going to use as a benchmark for some of these slides that are coming up. This is the LunaMap mission where we provided 112 watts onto a 6U bus, as you can see. And there's also included the SATA that I was referencing. That's in the image on the left, it's the gold square at the bottom, and in the image on the right, it's the black square that's in between the 2 wings. And the SATA drives both wings simultaneously. So again, that was 112 watts for the cells that were available at the time. But as the topic of this discussion says, we're looking for ways to deliver more. So how can we provide more power into relatively the same stowed height of that we've done for our classic Hawk designs, but get more power into 6U, 12U, 16U CubeSats that are canister deployed. So we looked for ways that we can further optimize our Hawk designs. In the image on the right, I'd like to point out, if you can see my mouse, I'm not sure if you can see that or not. Can you see it? Okay. I have a graphic here that shows a Hawk wing stowed on the side of a 6U bus, and you can see some envelope available around the outside that is unused. So I mentioned that was 112 watts from our LunaMap solar array, which is a good power packaging for that small 6U bus. However, we're not using all of the available footprint. We're stowed on this side of this face, but there's opportunities to grow and be more efficient. This design used 7 cells per string, and as you can see, we had 2 strings per panel, and all 4 panels were stacked on the same footprint. This used a standard cell size of 27.2 square centimeters. And if we look at our fill factor on this available footprint, we were only using 381 square centimeters of active cell area out of 778 square centimeters that are available. I'll show you where that 778 comes from in the next slide. It's actually the 12U bus, on a canister deployed 12U bus. One of the faces is smaller area than what you see here in the 6U example. So some of the opportunities that we identified for increasing power is, the first one that comes to mind is, well, put another string on there. Go 3 strings wide instead of 2. But for that cell size that I mentioned, unfortunately, that only fits on the top, which in the images on the right here, I have that labeled as 876 square centimeters available. And with that standard cell size, you can fit 3 strings wide on that face. But on the opposite face, or on the side faces of a 12U, you're more constrained in the available footprint, and those 3 strings wide just don't fit without relying on the canister itself to hold that wing in place. And our design relies on a perimeter launch restraint, which you can see in that top image here along the edges. The silver feature that you see is an edge restraint that we use. A lot of solar arrays will use a constrained, discrete hold down, usually right around the center of the wing, which takes away some of the active area available for cells, and it can make the packaging efficiency a little challenging. But MMA has developed, as part of this Hawk architecture, a very low profile, very efficient perimeter hold down that clamps on these long exposed edges, and the launch restraint device resides up at this end, which is opposite of the root hinge, obviously down here where the SATA is. And an enabling feature of this launch restraint, besides this low profile of where the actual clamping takes place, is the initiator for releasing this is a thermal knife, and it also has a very, very low profile. So as presented here, no features of this stowed array assembly penetrate the bus surface. This is all stowed in the area above the bus interface. If we were to switch to, say, a SEP nut or a frangible type launch restraint, those have significant height, and we would require some internal envelope from the bus to accommodate that launch restraint. And we have done some Hawk designs with that where a customer preferred that style of launch restraint device over the thermal knife. But the thermal knife is our baseline because it's just so efficient, and it allows us to not penetrate the bus anywhere. So I mentioned one obvious approach would be make it 3 strings wide. Well, that only fits on one surface if you want to rely on a launch restraint system other than the canister, which if you rely on the canister, that means every time you're handling the bus outside of the canister, you're at risk because the panels aren't very well constrained. You have to have some additional tooling available to hold those panels in place and support them until you place it into the canister, and then only then are they preloaded and in a nice, stable, secure configuration for launch. So there's some risk involved in that, as well as snag potential in the canister. You're deliberately contacting the inner walls of the canister to keep your wing compressed, and there's some risk there during deployment that you might catch on something on those inner walls. So that deployment can be tricky. We've done it. We did it on a program called BioSentinel, and we used on two of the bus surfaces, we had our Hawk array that was with this rail system of launch restraint that I described, and then on the other 2 surfaces, we had 3 strings wide, and it was deployed as it came out of the canister. So the canister walls were compressing the panels on the side. So it can be done. We've done it, but we tend to prefer having a commanded deployment so that there's no risk of interference during deployment, and you can deploy the wings when you're ready to deploy the wings, not necessarily immediately as it comes out of the canister. Another obvious opportunity would be increase the cells from 7 cells to 8. Now this is obviously bus power system dependent. You need to make sure that the bus system was designed for that increase in voltage. The voltage of a given string is determined by the number of cells in the string as well as the cell type. 4-junction cells tend to have higher voltage than a 3-junction type cell, for example. And we can often tailor the voltage of the system by adjusting the length of the string or changing the different cell types, selecting from different cell types that are available to tailor the operating voltage to match the bus. But if we assume that we can go ahead and increase it from 7 cells to 8, that's no problem. There's actually enough room down here on the end that we can add an 8th cell. But what would be really nice is if we can use a custom cell size that would allow us to optimize this footprint and fit on any side of a 6U or a 12U bus. So that was our goal. And with support from AFRL, we were able to do a lot of this development work under an SBIR that they had funded. So we thank AFRL for their support on that, and the results that you'll see in these upcoming slides really came out of that effort, working with AFRL to further optimize and improve these already very efficient Hawk arrays. In addition to power output, we're also looking for ways that we can provide more in terms of less assembly time and less cost. How can we get more efficient and improve our production and our design methods that we use here at MMA? And one of the areas that we identified is the installation of the panel wiring and the wing level wiring. This can be a significant amount of touch labor. Routing the wires around, staking them, ensuring that they're not obstructing the cells in any way, and then performing a soldered or welded connection. It all takes a significant amount of time. So we put some effort into developing a method that includes at least the panel level wiring in the panel construction, whether it's a printed wiring board type construction, like a circuit board, like you'd find in your home computer, or a flex circuit that is incorporated into the insulation layer that we put on all of our panels anyway. It's usually a Kapton layer that's on top of the substrate that provides electrical insulation between the strings and the grounded substrate. And we can build flex circuits into that Kapton layer and save ourselves quite a bit of design and installation touch labor time to be more efficient, so we can release the design faster and we can assemble it faster and at lower cost. This would still require some discrete wiring at the hinge lines and certainly as it comes off the root of the wing to connect to the bus. But this is a significant reduction in the amount of wiring that is actually on the wing. So we think this is a good opportunity to save some cost and assembly time, design and assembly time. Furthermore, we want to look at ways to improve our reliability and our lifespan. CubeSats are continuing to grow in terms of mission capability and mission endurance. I mentioned Marco was a pair of CubeSats that went to Mars, so we've already demonstrated interplanetary travel. But CubeSats, while initially were limited to a few months in low Earth orbit, now we're seeing applications where we're doing electrical orbit raising from LEO to GEO or going straight to GEO and spending more than a few months, in fact, spending several years. And the capabilities of the instruments that are on the CubeSats are growing as well. So CubeSats are beginning to replace what smallsats used to do. And along with that, we need some improvements in reliability. Now, all of Hawks used to date and flown to date, and all the future ones that we're doing, have always used welded string assemblies. So I discussed the string earlier. That's the number of cells that are arranged in series, and each cell-to-cell connection is welded. However, historically, all of the Hawks at that point have transitioned to a soldered connection, and the panel wiring that I discussed just a few minutes ago, we would make those connections with a solder joint. And this is fine for 5 to 8 years in LEO orbit, but we're seeing mission requirements that are growing beyond that. And as I mentioned, looking at GEO orbits or deep space opportunities. So soldered connections can be very good for short duration missions and with limited ranges of thermal cycling, but they do degrade in performance over time. Welded joints, however, have been demonstrated to be very reliable in harsh environments and very long duration missions with large ranges in temperature. So MMA is also working towards transitioning all of these solder connections over to a welded connection so that we can provide a fully welded or crimped. Crimped connections are also proven to be very reliable. So we're working to eliminate these solder connections so we can focus on move towards a fully welded assembly and provide better reliability and lifespan. And that all of the missions would benefit from that point forward. Even short duration missions we would be able to provide with a fully welded assembly. These efforts also were supported by FRL on that SBR that I mentioned. Also want to point out in this image, on the previous slide, I had talked about a restricted area of 778 square centimeters. So I want to highlight that that's actually the side surface of a 12U CubeSat. So as we're optimizing the cell size, I mentioned we want to make sure that we can fit this assembly on any of the 4 faces. So you could have an optimized cell size for this top surface and a different size for the bottom and a different size for the side. But to be efficient, obviously, we want to, when we're going to invest into this custom cell size, we want to do it wisely so that we can fit on any of the 4 surfaces. So comparing to LunaMap, as I said, this was a configuration that used a 27.2 square centimeter cell as a standard cell size available in the industry, and it was 7 cells per string, but you could also wire that panel up as 14 cells per string. And based on that 778 square centimeters, we were only providing in our stowed footprint about a 49% fill factor. As efficient as it was, half the area wasn't populated with active cells. So certainly this is a ripe area for improvement. If we use an optimized cell size, a custom cell size, now we can fit 3 strings wide, like I mentioned earlier, and it fits on any side of a 12U bus, and we have a little more flexibility in the string length. In combination with changing or selecting different cell types, whether it's triple junction cells or the emerging 4-junction cells, and looking ahead to some of the emerging technologies that are coming out, we can mix both the cell type and the string length to be more accurate in our tailoring of the voltage requirements for the bus. So with this layout, we also made sure that the center string, we had enough room on the ends that we could split this 8-cell string and create 2 4-cell strings. So that allows us to have an 8-cell string or a 12-cell string or a 16-cell, or even make the whole panel 1 string of 24 cells. So we have more flexibility in string length. And now we're using 77% of this available footprint. When we're stowed, 77% of that area is actually cell area. It's not 100%, even though it's obvious it's optimized, but because we still need some substrate area for the wiring, and we need area for the launch restraints to sit, and the release mechanism. So we're not able to get up to 100%, but we did improve our fill factor from 50% to 77%. So it's almost a 50% improvement. And this is just changing the footprint. We didn't impact our stowed height at all. So same stowed height as what we had in the LunaMap design. So if we compare those 2 designs on a power perspective, this is at the beginning of life, peak power, M028C. With that LunaMap design, if we could have configured that in a 3-panel arrangement, or as I showed, it was a 4-panel arrangement, our power would be 84 watts or 112. So 112 is what flew on LunaMap. It had that 4th tip panel to it. If we had this technology available at the time, this custom cell size and this wing design, we could have provided over 124 watts with the same cell on a 3-panel design, which would have exceeded what we provided on our 4-panel design. Or if we had done a 4-panel design with this optimized cell, we would be over 160 watts. So it's a significant improvement just by using the rest of the available footprint that was already there. If we use a newer cell type, we can get even more power out of it. The solar cell industry is always very competitive and always improving year to year with new technologies and improvements. I mentioned going from triple junction to 4-junction, but even within the triple junction family, year to year there was a quality improvement and performance improvement from the cell suppliers. So if we were to use a more recent cell design, then these are the numbers that you could realize for these various configurations. Obviously, it's a very modular design, ranging anywhere from a single panel per wing to the 4 panels per wing that I mentioned. And you can also combine them with on the other sides of the bus to get significant powers up over in excess of 350 watts on a 16U bus, canister deployed. If we're outside of a canister, then we have other options available, and we have developed and provided flight solar arrays for CubeSats, but they're not in a canister, so we don't have that constraint, and we were able to use larger cells to realize over 200 watts on a four panel wing, pair of 4-panel wings. But this presentation is focusing on the improvements that we can do specifically towards canister deploy because they're so constrained on their footprints. But this as the slide shows, there's so much flexibility in what we can design. I mentioned already the string length flexibility that we have available. We have developed this custom cell size with multiple suppliers, so we have multiple cell types available that we can use to tailor the design for your specific mission. Development status, the substrate and mechanisms are carried over directly from our legacy Hawk designs. So those are already tiered on, as I mentioned, we've flown on several missions. So no changes to the substrate or the mechanisms. The integrated wiring, whether it's a printed wiring board or a flex circuit, we have developed both of those and demonstrated them successfully. With the flex circuit design was delivered several years ago on a flight mission. The custom cell design is complete for both a 12U or 6U and a 8U or 16U. Those are two different cell sizes, custom cell sizes, so that we can take full advantage of that available footprint on those two different standards. The welding development, I mentioned earlier, all of the strings are already welded cell to cell, and we've completed our string to circuit connection welding development on the printed wiring board. The flex circuit is still in work, but we're working on that. And we have built and demonstrated a 2-panel deployable prototype using this architecture. The next big step is obviously awaiting system qualification. We have a mission that we're anticipating to start this year that is going to use is baselined using these custom cell size. So we're anticipating that we'll be able to further the maturity of this design as a benefit of that program. This table shows a variety of different Hawk designs that we've completed. For some have flown, some are waiting to fly, and I want to point out over here the optimized rows. These are the ones that use the custom cell size. Whether it's on a 6U or 12U, you have a 2U by 3U footprint available to you, and so these are showing the performance if we use that optimized cell size. 2x4 is obviously an 8U or a 16U bus, and the powers that are available. This table is available in our brochure, which is also available on our conference website. Sandy has a link on there that you can click on to download our current brochure. And in there, you'll find the same table. So you'll have this available as a reference. So as a summary, the advantages for these changes these improvements that we're making in the EHawk design, where I should have mentioned the E in EHawk means enhanced Hawk. The original Hawk was designed to fit on the 3U footprint with a side of a 6U bus. So it was a single string per panel, and that was the original Hawk, high watts per kilogram. The enhanced Hawk simply means more than one string wide, whether it's 2 strings wide or 3 strings wide. So the Luna map is an EHawk design because it has expanded beyond that single string per panel architecture. With this custom cell size, we're able to optimize our active area for a given panel size and maximize that fill factor for both 6U and 12U, as well as 8 and 16U buses that are canister deployed. This allows us to provide approximately 48% more power than our legacy EHawk designs. So a significant improvement without changing the cell type at all. All we've done is optimize the size of the cell, and that allows us to get approximately 50% more power out of the same available footprint on the face of the bus. As I mentioned, we can tailor the string lengths. We have quite a bit of variety in the string lengths available. We're working on incorporating the panel wiring into the substrate design to reduce the touch labor and design and manufacturing time. Also investigating printed wiring board type construction, which can come up with further cost and schedule reductions. However, they tend to be a little less mass efficient based on the materials that are available in the printed wiring board constructions. And we're also working towards eliminating the solder connections so we can provide improved reliability and longer lifespan for harsher environments as the CubeSat missions mature and become more challenging for the solar arrays. I also want to talk a little bit about how we can leverage these CubeSat technologies towards larger satellites. I understand this is a CubeSat developers workshop, but I think there's value in showing how this technology that was developed specifically for CubeSats can also be leveraged through higher power systems and larger buses for larger missions. And one way we can do that is with this architecture that we call the Armhawk, which stands for rectangular hawk. It is a truss deployed system, but it takes those same thin substrate panels that we just covered in the Hawk development, and it allows us to deploy a large quantity of those in a blanket type arrangement. If we look at the Hawk arrangement, you may have noticed that we go up to 4 panels per wing. We have looked at some designs that have 6 panels per wing or a little more. However, that tends to be very mechanically complex, and it becomes the deployment risks and reliability tend to suffer with the greater number of panels that are all deployed off of a common root hinge. So there's a natural limitation in the number of panels that you can reliably and effectively deploy off of a common root hinge line with a self-supporting rigid panel type architecture. If you want to go larger and have more panels, a blanket type arrangement is the natural progression. And this is where there's a truss that you can see in this view on the right. There's a 3-longeron truss behind several thin substrate panels. So imagine these panels are the same construction and they're hinged together using the same hinge architectures that we have on our Hawk arrays for CubeSats. But this allows us to stack dozens of these panels in an accordion folded stack. And then it can be deployed with side panels just as like we used on the Hawk arrays. We had not just the center panel, but you notice that there were some panels that we deployed to the side or off of the tip. So we can use that same architecture as these center panels deploy. They can release these side panels to further expand our footprint as we deploy. Furthermore, this entire wing can be mounted onto a SATA, just like we've done with our small CubeSat arrays. So the truss assembly down at the base would be mounted onto a SATA, and upon deployment, could be rotated. In this architecture, it's not a tension blanket, and I'll get to, I have a slide coming up that will compare the Armhawk blanket to a tension blanket. But as I mentioned, these are rigid panels, so they don't need to be tensioned. They just need to be supported and deployed. So each pair of panels, the hinge line on each end attaches directly to a batten frame. That's this in-plane triangular shape structure on the truss. And we can attach these hinge lines directly to that batten frame. And every other hinge line attaches directly to the truss. So it becomes a distributed mass along the length of the truss. Also in classic tension blankets, the blanket material tends to be very thin and naturally very flexible. Unfortunately, that doesn't tend to provide very good radiation shielding. Since we're carrying over these thin substrates from the Hawk design, we maintain that backside radiation shielding. The cover glass protects the radiation from the front side onto the cell, and the substrate needs to protect the backside of the cell because radiation comes from all directions. So we're maintaining that good radiation shielding of these thin substrates. I'll play this video while I talk through this slide. This is a video of a deployment of tape spring longeron architecture used for a deployable truss. And this was also developed for a CubeSat. We started with a challenge under an SBIR for developing a 100-to-1 expansion ratio, that is the deployed length compared to the stowed length of the truss, and to deploy that out of a 1U volume. And we were successful with that. So that's 10 meters of length deployed out of a 1U volume. And that's the design shown here on the right. The longerons here is what's enabling for this very high expansion ratio. And I also want to point out that notice there's no canister like you may find in some other truss architectures that are common in the industry. There's no surrounding canister, so our stowed height can be very, very short, just the height of the drivetrain and the stack of the batten frames. And on the right here is an example image of what we call our tape spring deployment assembly, which is the TDA. So there's a motor drive system in here driving out a composite tape spring, and that tape spring becomes the longeron of the truss. What you can't see in this video, I'll go ahead and play it again, is the tension diagonals, but they're highlighted over here in the graphic on the right. So it's a classic deployed truss architecture, tension compression. The longerons are deployed and placed in compression, and the diagonals are placed in tension. And it's a rigid batten frame design, so our cross-section does not change between the stowed configuration or the deployed configuration. There's no canister, so we can attach payloads at any point along the length. I mentioned on the Armhawk, we use that to our advantage to attach every other hinge line to these batten frames. But this boom design could be used for attaching other instruments along the length. So this architecture was developed for CubeSats, but it's very scalable. We're using it on a current mission that has a diameter almost 2 meters in diameter. So it's a very large truss system leveraging the same technology. Oh, thank you. Sorry about that. So it's a very scalable architecture, but the expansion ratio is what's truly the most enabling feature of this, and that's what allows us to be so efficient with this Armhawk. No canister, very short stowed height, very high expansion ratio. In this view, I'm showing it installed on a typical ESPA bus envelope. And what I'm showing in these extra pie envelopes is if you look at the ESPA ring and you draw a line from the center of the ESPA ring and you contact the front corner of the published bus envelope or payload envelope, there's some bonus envelope here that you can get if you just ask for it. So what we decided to do was see how much power we could fit into this available pie wedge on the side of an ESPA bus. And we were actually able to provide over 6 kilowatts of power just in this available pie wedge envelope without penetrating into the bus other than the depth of the SATA itself. This particular one that I'm showing here is a 1 kilowatt wing. So this is a 2 kilowatt system. But here you can see the triangular bus is stowed next to the stack of thin panels I described that are carryover from our other Hawk designs. This is a view showing it deployed, and this is a 1 kilowatt wing. And down here, these circles are highlighting every other hinge line where it attaches to the truss. So this deployed solar array blanket effectively behaves like a distributed mass along the length of the truss. And each of these hinge lines is spring driven using stored spring energy. So, and those are designed just like we do on our Hawk arrays so that the torque provided by those hinge lines is sufficient to overcome the parasitic torque of any harnessing. And we can pull the harnessing off of these panels at any point along the wing and transition it over to the truss structure. But each hinge line is designed to overcome its local parasitic torque requirements such that the truss itself does not need to tension the array in any way. Just released freely, all of the panels would deploy to a flat condition and overcome all of their parasitic torque just using the integrated hinges that are already on there without any additional assistance from the truss. What the truss provides is mechanical sequencing during deployment, and it provides that backbone support structure that the panels are mounted to. This is a slide showing that deployment sequence that I just tried to describe. So So we start off with it stowed, and then as the truss is deploying, every other hinge line is attached to the truss. The truss is providing a mechanical sequencing as the stack expands. And as panels approach a flat condition, they are able to release these side panels that I had described and that you had seen on the earlier Hawk architecture, so that we can further expand our available footprint. Once we're deployed, if we're mounted on a SATA, at that point the whole wing can be pointed by the SATA. I mentioned I had a slide on comparing us to a tension blanket, and that's a natural comparison. When you look at this, it looks like a blanket architecture, but it's not a tension blanket architecture. As I described, these are rigid panels. They're self-supporting. All they need is a backbone behind them to attach to, so that it's not a classic rigid panel wing that is only secured by the root hinge. This is a truss-supported architecture. In a tension blanket architecture, the blanket is only attached at the root and at the tip of the boom. And the first mode is dominated by that blanket frequency. It's a guitar string behavior. The more tension you put into it for a given mass of that blanket, the higher the frequency. So you could change the depth of the boom, the truss that is supporting that blanket, and it would have no effect on that first mode of the blanket. The only way to improve the first mode of the blanket is to increase the tension, which naturally would require a more robust truss. The truss can only be as robust as it needs to be to provide that tension. You can't realize any first mode benefits beyond that. With our architecture in this Armhawk, the truss is the primary structure, and the array is just distributed along that structure as a distributed mass. Therefore, we can directly change and impact that first mode frequency by changing the diameter of the truss or changing the materials of the truss. It's not a tension dependent frequency. It is a structural frequency. So we have a lot more flexibility in how we can tailor that first mode. I also mentioned that tension blankets naturally need to be very flexible, so they're using materials that are very thin and unfortunately do not provide very good radiation support on that backside. Since we're carrying over all of these rigid substrates with thin substrates, thin solid substrates from our Hawk designs, we preserve all of that radiation shielding on the backside. We can take some of the truss mass and robustness that would be necessary to tension a large array. We can take some of that mass out of the truss and put it into the blanket or the panels so that we can have that radiation shielding on the panels. And then make sure we still have the strength and stiffness that we need from the truss by leveraging the geometry, something that a tension blanket doesn't benefit from. Since we don't have a canister, our packaging efficiency is outstanding. On a classic, like on the space station down here, those were canister deployed trusses. And when you looked at the stowed envelope, the arrays packaged very, very efficiently. And then next to it was a very large canister for deploying the truss. With this truss architecture that I described, there is no canister, and we have an extremely high expansion ratio. So our stowed envelope is now very, very small. And as I showed on the ESPA example, the stowed height of the truss was the same height as the stowed panels for the array. So it's very efficient. And it stows into essentially a rectangle, or a rectangle with a small envelope for the truss off to the side, which is very friendly for fitting into the available envelopes on the bus. With some arrays, for example, the ROSA in the bottom right corner, when that rolls up, it naturally rolls into a cylindrical type of envelope, which can be difficult to fit into available envelopes on a bus, because the diameter of that stowed envelope is your stowed height. In our case, with the Armhawk, we can have a very short stowed height because of the truss architecture. So in conclusion, the packaging efficiency of the Armhawk is what really stands out. And the state of the art is typically around 120 watts per kilogram and about 40 kilowatts per cubic meter. The kilowatts per cubic meter is a metric for the total power, peak power of the wing, divided by the stowed envelope of the wing. That includes the truss and the launch restraints and everything. And the classic metric is about 40 kilowatts per meters cubed. The Armhawk, because we don't have that canister, because we have such an efficient truss architecture behind these very thin substrates that are self-supporting, we can actually exceed 90 kilowatts per cubic meter, so twice the industry metric. And 120 watts per kilogram is a good target for current state-of-the-art blanket type arrays. And with the Armhawk, we're right there. We're at about 130 watts per kilogram. And on that metric, I have to go up here real quick to this table and point out, notice that the classic Hawk is also running in excess of 100 watts per kilogram. That's our metric for calling it a Hawk, high watts per kilogram. But we also have some tricks that we can do on the substrate design to achieve an even higher mass efficiency, and that's what you see in this high performance column. We've made some changes to the substrate to further optimize the mass for a given stiffness, and that's how we're able to exceed 130 watts per kilogram, in some cases even over 150 watts per kilogram. That's very difficult to find in our industry. And this larger scale, now we're talking multiple kilowatts, and we're still able to hit over 120 watts per kilogram. All of this architecture, is leveraging high reliability heritage materials, processes, mechanisms that already exist and have flown for on our Hawk arrays for CubeSats. This is all born out of that CubeSat technology. We retain the rigid substrates, as I've said several times, to preserve that radiation shielding that is so critical for long duration missions or in high radiation environment missions. The structural depth is actually directly related to the first mode, so we can use that to tailor the stiffness and provide a high stiffness and strength. It's canister free, which is critical for that expansion ratio that I said, and minimizing that stowed envelope, maximizing that kilowatts per cubic meter metric, and it's very scalable. I showed you a 1 kilowatt example, 1 kilowatt wing example on an ESPA bus, but we have been able to fit in excess of 6 kilowatts on a pair of wings in that same envelope. So that concludes my presentation, covering both the improvements to the existing Hawk design as well as showing how we're leveraging those technologies going forward into larger systems. So now we can open it up to a Q&A session, and as I mentioned, Andrew Haynes is here with me to assist with answering those, and hopefully Sandy has been fielding those questions on the side.
Yes, we have been answering some questions. One question that's currently out there is, what's the current TRL of the Armhawk?
The Armhawk is the truss design itself is TRL 6. We have not integrated the wing assembly onto that truss prototype yet. So as a system, it's at TRL 3. If you look at specific components or subsystems in there, there are areas that we can claim TRL 9. But the overall architecture is still at, I think, TRL 3.
Do you have any possible tech demo on the horizon where you think you'd be able to fly it, deploy it?
The Armhawk or this?
The Armhawk, yeah, the Armhawk.
We have submission opportunities, but we don't have any on the books at this time. So we have several opportunities out there that we are chasing, but unfortunately at this time I don't have a launch date that I could provide for that.
Yeah,
or you're saying about that demo, say.
What about a similar question on just integrating kind of the arrays to the truss? You said truss TRL 6, but you haven't integrated arrays. You have a plan to do that on the ground to kind of raise that system TRL? Yes,
we have a marketing type that has panels attached to a very simplified truss. So naturally, our next step is going to be to take some representative panels and hinges and attach them to that truss prototype that I showed. So we do have a plan to do that. Unfortunately, I don't have a timeline on when we'll have that completed and when we can share some updates on that. But that is our next step, absolutely.
Great, thank you.
Yes.
This was very exciting because what I've seen as a trend is that we are looking more and more at ESPA-size crafts, and then we would allow, that would allow space for more instruments. So having more power is always a good thing. So we'd like to see how that is possible. Even at 500 watts, that would already be a good thing.
Yeah, we definitely see this as a game changer for fitting a lot of power into a small envelope. That's the key metric of kilowatts per cubic meter, and that's where the Armhawk really shines. If you compare mass, and it's very similar, as I said, the watts per kilogram, we're right up there with the ROSA and Ultraflex. So we're in the same class of mass efficiency. It's the packaging efficiency and the radiation protection that differentiates the Armhawk from those other competing technologies. And we think that is really very enabling for these missions, because it frees up more space in the bus for you to have other instruments and other capabilities on the bus.
Sure. Also, people talk a lot about cell efficiency, like that can change the math a lot, right? And you mentioned that you have one supplier with multiple designs or multiple suppliers. So what is the state of the art now in efficiency? Is there a specific model? Has it been flown? So where is the latest technology right now in cell efficiency?
For existing fully qualified designs, that's the 4-junction design, and that is in the 30 to 32% efficiency. So the chart that I showed that had the multiple configurations, the numbers that are in here are for a 32% efficient cell.
Okay. Thank you.
Sure. And yes, we work with all of the major cell suppliers, and all of our designs are cell agnostic. One of the first things we do when we're working on a new design and we're working through a specification, it's trying to tailor the design to maximize our power output as well as optimizing the voltage. So we're always trading the different cell types from different suppliers. All the big suppliers offer, for example, a triple junction cell. But a triple junction cell from Spectralab performs a little different than the one from Solero, which performs a little different from Azure. And then there are some other emerging technologies in the silicon and perovskite type cells, and MMA's Hawks have always been cell type agnostic. So we can always choose the best cell for your mission.
Okay.
Yeah, so how flexible are you as far as being able to adjust the voltage or being able to backwire them or make them magnetically neutral?
Right, for magnetic moment. So our standard process here, without being directed to do additional lengths, is to run the backside wiring so that we minimize the magnetic moment on any given panel. Often a specification will come in and say that we have a magnetic moment requirement for the array, but that could allow you, if you have a pair of wings that are canceling each other out, you could potentially have a noisy wing that is being canceled by another noisy wing. And it's a noisy environment, magnetically speaking, but it cancels out to a near zero moment. However, if you lose a string or you lose a panel or several strings, that could dramatically change that magnetic moment. So a standard process, MMA is always striving to minimize the magnetic moment on a given panel, so that if we were to lose a string, that we would have a minimal impact on that near zero magnetic moment on the array. The flex circuit technology that I talked about, or the printed wiring board technology, offers additional benefits by eliminating the thickness of the substrate from that calculation. When you're calculating the magnetic moment, you need to look at it in all three axes and come up with your net moment that comes out of it. So the thickness of the substrate often comes into play because the traditional discrete wiring is run on the back side of the panel, tracing the back side of the string as it's routed on the panel. And that separation between the wiring and the string, now on these Hawk arrays, it's a very thin substrate, but on some of the larger arrays, it might be a sandwich panel construction, and you might have significant distance between those two, and that can create a problem with magnetic moment. So these technologies that we're developing to bring that backside wiring to the front side via flex circuits or printed wiring board approach are all directly beneficial to that magnetic moment performance.
Do you think you can get it quiet enough, or have you been able to get it quiet enough to support magnetometers or maybe even differential GPS antennas or something? This is something at the very far edges. Having a mast that long is really tempting for a lot of instruments.
You're speaking specifically to the Armhawk architecture. So
well, the Armhawk, actually, either of them. But yeah, if we have a deployable mast like that, it would be hard to keep our scientists from wanting to put something on it.
Yeah, well, if necessary, because of the modularity of that design, the array, if let's say the magnetometer is on the tip of the mast might be longer than what we need for the array. So depending on the power requirements, say the array only takes up half of the mast length, and then the magnetometer is deployed an additional length beyond the end of the array to get some additional separation from the noise of the array. That could be beneficial as well. But all of these technology improvements that I talked about are directly applicable to the Armhawk, so we can drive each panel to a near zero magnetic moment. Now, we haven't had you asked if we had a mission specifically that uses a magnetometer, and that I don't know, because it's not often conveyed not always conveyed in the specifications that we receive. But we have received specifications with very demanding magnetic moment or magnetic field strength requirements on those. So we're familiar with designing to those types of constraints. But I think it's important, there's value in realizing that you're not constrained to the length of the array, right? The truss could continue, and we could push that magnetometer even further away from the bus and further away from the array, assuming it's a common structure.
Okay, great, thank you. And when you print the arrays, is it possible to adjust the number of strings for to increase or to change the bus voltage? So if we have an instrument that requires a non-standard bus voltage, and we need to increase it or something, we actually had that come up last year. Would that require just changing some printing parameters, or is that a whole redesign effort now?
Well, to be clear, there's no printing happening in here. I'm not sure what you're referring to there. But what we
I misunderstood you. I thought you were saying we're talking about the back wiring being printed.
Oh, so you're referring to the flex circuits?
Yes.
So
well, either way, however you determine the number of cells in a string.
Yeah, the flex circuitry isn't what would be limiting there. What we would do is look again at the cell types available and compare that, trade that with string length to find the optimal solution, because what we're trying to fit it into, so on the Armhawk, you're not constrained to, in these examples here, you're constrained to the available footprint on the canister deployed. If I go down here to an Armhawk, your footprint available might be less constricted, you have more available. So now what we're looking at is trying to fit that string, that single string footprint, that area, like a Tetris piece. We're trying to fit several of those strings onto that available envelope of the panel while managing stay-out zones for launch restraints or hinges or sun sensors, other features that might be on there. And we're always trying to optimize to how many, so we can get the most active area of the cell for that available space, maximize that fill factor. And so it's the string area that's driving it. Initially, you might think, well, bigger cells are better, right? You can get more efficient packaging with bigger cells or smaller cells, and really, it's not. The cell size is only a part of the challenge. You need to tailor the string footprint, the string area, so that you can fit the correct number of strings onto that panel and maximize that footprint. So if your string is just a little bit too long and you can't quite fit that last string in there, the whole string goes away and has to move to the next panel, and that's not very efficient. So we'll look at all the knobs that we can turn so that we can maximize that power output for a given panel, which then transfers obviously into a very efficient array for those panels. So we'll trade cell types and the cell size and the number of cells in the string to get you that maximum. And then once we have the string layout, then the wiring is of course tailored to match that string. One other thing I wanted to point out is sometimes it's a body panel versus a deployed wing, and you have different temperatures, but you want the arrays to be operating in similar voltage ranges. So we've had designs in the past where we've had to use a different string length on the body mounted panel because it was seeing different temperatures than what the wing was seeing. And that way we were able to optimize the power output and the operating voltage for the two different temperature environments of the panels. So there's a lot of flexibility and a lot of knobs that can be turned when we're tailoring these custom arrays for a mission.
Well, thank you. Thanks a lot.
Sure.
So I have a little bit of a tangential question. I know a couple years ago, MMA was also offering some limited antenna design, antenna arrays that would also ride on some of these solar cell deployment mechanisms. And I didn't know if in the last year or two, have you had any calls for that type of a design, like the IRL maturations, that sort of stuff? Are you still offering antennas as well on these,
Yes.
this type of deployment?
Yes, we are still developing antennas, and as you pointed out, this Armhawk architecture, in this case, it happens to be deploying solar panels, but it could also be deploying an RF panel instead, or some other instrument on there. So it's a versatile architecture in that respect. And yes, we are developing deployable antennas. We have some other sessions this week that speak specifically to that. So, Sandy, do you know what day and time we have the antenna specific? Oh, okay. So the answer is yes, but I want to get you some more information. We have some talks coming up that are specific to our antenna developments.
Thank you. I will send you an email. I may or may not be available. I know I signed up for a couple of your talks, but in case I'm not available, I'd like that slide package. And since you are familiar with both designs, another question that often comes up, you know how solar panel runs hot and usually that degrades antenna performance. Have you ever tested any kind of degradation or interference? Just what if one would put just an antenna on, just on in the midst of solar cells? Like what kind of interference that would cause? Did that ever come up? So let me rephrase. Sometimes because of space constraint, we run out of body space on a CubeSat, especially if you want to carry 4, 5, 6 antennas on all different faces. And sometimes as a last resort, we would say that, oh, let's put an antenna right in the middle of the solar panel. And so I'm trying to ascertain if that, if anybody knows if that would cause any kind of pattern degradation on the antenna because of the naturally hot temperature of the solar panel.
Well, the temperatures can be can be moderated by the finishes that we put on the panel on the back side. We've done some different coatings on the back side of the panels to try to optimize the temperature performance. I think more of a concern would be any blockage effects, making sure the antenna has an unobstructed view, and likewise the antenna isn't casting shadows onto the solar array. But with the solar array being a DC device and the antenna not, they tend to be quite compatible. I know there was a mission recently where they had a solar array on one side of the panel and the antenna was on the other. The name is at the moment, but they can play well together. They often aren't trying to point in the same place, though.
Yeah.
Antennas are trying to point down at Earth where the solar rays are pointing towards the sun. So
Yeah.
that could be a conflict more than anything else.
Okay. Well, thank you.
Sure. That's today at 2 o'clock? Mountain time. So we have an antenna presentation today, if you're able to make it, at 2 o'clock Pacific time. But if not, please, by all means, reach out to us and we'll get you the information.
I don't seem to have the invite for the 2 o'clock.
Yeah, you can find information in the chat.
Okay. Are you able to access the chat window of this meeting? I understand that there's some information in there. I'm not able to see it as the presenter. Or reach out to us here at MMA and we'll get you the information.
Okay. Thank you.
Sure.
We have a question from Benjamin. You speculate on that potential simplex proposal call coming sometime next year for an Armhawk solar array?
I think it would be good to follow up with us directly on that one.
That's
so I'm gonna.
Benjamin.
Okay. So Ben, yeah, let's talk directly about that one. Okay, we've exceeded our time here. Is there any other outstanding questions? Maybe we can take one more. And
No, that was it. Thank you. For me.
sure. Thank you everyone for your time. And as I mentioned, by all means, reach out to us if you have any other questions or you think of something later on that you wish you would have asked. Please reach out to us. We'll be happy to get back to you and answer any questions that you may have. So thank you very much for your time and enjoy the rest of your day.